Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to talk about axiomatic systems. As you may remember, the current module that we're on is about axiomatic systems, so this is a very important topic for us. In this video, what we'll do is we'll explain what an axiomatic system is, and we will talk a little bit about a simple example of one, something called an incidence geometry. That's precisely the kind of axiomatic system that you have a proof to write for in your first mastery homework due this coming Tuesday. Okay, let's talk about axiomatic systems. So the first thing I want to point out is that we have a difficulty making a clear definition. What is a point? What is a straight line? Both of these objects are of fundamental importance inside of Euclidean geometry. What are they? What's a reasonable definition of them? Let me let you think about that for a moment. Feel free to pause the video and see if you can come up with some ideas. Now what I'm going to do is I'm going to tell you what Euclid had to say. So Euclid defines a point as that which has no part. To be honest, I find that a little bit hard to work with, but I think it catches the intuition that we have that a point is just a dot. It has no substance to it other than its location. It doesn't have any thickness, it doesn't have any width, it has no part. Okay, what is a straight line? Well, what Euclid says is a straight line is a line which lies evenly with the points on itself. I think this is trying to make an intuitive idea of what straightness means. But as an actionable definition that you can use to check something, it seems like a very difficult object. Now, what we defined in week 1 was we said that a line is the shortest path between 2 points. That works fine if we're defining a line segment, but it doesn't work so well if we're trying to define an infinite line. The other problem is, as we saw in agonizing over what happens on the sphere, or in taxicab geometry, or in Euclidean geometry, is we still need to make a definition of distance, because this notion only makes sense if we have a notion of what a shortest path is. In the absence of the notion of a shortest path, this definition is not workable. Okay, so what can we do? We can do a classic mathematical trick, which is we're going to define the problem away. And we're going to encapsulate the problem. And then once we have it encapsulated, we're going to work with it in a broader context. So here we're going to say an axiomatic system consists of a collection of undefined terms. Now the reason we're doing this is we're going to want to make a point and a line to be undefined terms, and then make sense out of what happens with that. Then we're going to have a list of what we call either axioms or postulates. These are going to be statements about the undefined terms that we're going to take to be true basically by definition. We're going to declare these statements to be true within our axiomatic system. I should say something about the vocabulary. Axiom is maybe a more modern mathematical term. It's used quite frequently across all of mathematics. But a postulate is used quite classically in geometry. Euclid used the term postulate. I believe there was a historical distinction between axiom and postulate. In modern mathematics, they're synonyms, and in this class, they're going to be synonyms. In principle, when we have an axiomatic system, we also need to specify some rules of inference. For us, we're going to take implicitly the rules of mathematical logic. So things like De Morgan's laws and things like that you learned in Math 305. Okay, as I already said, we're going to declare axiom and postulate to be synonyms, at least in the context of this class. Okay, so now I think we should do a little bit of review from Math 305. You may remember from Math 305, you talked about some mathematical logic. So we'll review some of it, and we're going to change the language a little bit. Okay, so the first thing we want is something we're going to call a statement in this class. In Math 305, you called it a proposition. I don't want to use the word proposition for this for historical reasons. A proposition means something else in the context of geometry. We'll get to that in a little bit. A statement is a declarative sentence that has a truth value. It's either true or it's false. Doesn't matter if you know if it's true or false or not. It just needs to have a well-defined truth value. So I have some examples here. 7 is an even number. That is an example of a statement. It happens to be a false statement, but it is a statement. It has a well-defined truth value. The 500 trillionth digit of pi is 3. I have no idea if that's true or not. Right? I don't think anybody knows if it's true or not. I don't think we know that many digits of pi. But it doesn't matter. Either it's true or it's not true. So that is a statement, even though I don't know its truth value. Now here are some examples of problems. 7 is an interesting number. That's a value judgment, right? That's not something that has a true or false value to it. And here's a more interesting example. 2x minus 4 equals 0. That is not a statement because its truth value depends on this variable x. So it itself is not a statement. Now, as you know, that kind of thing is the kind of object that we want to talk about a lot in mathematics. Right? We're interested in knowing about statements that look like equations, inequalities, things like that. So we're going to introduce a slightly broader class of thing we're going to call a predicate to be something that would be a statement, except it has a variable in it. In Math 305, you might have called it an open sentence. So it's called both predicate or open sentence. So in this example, 2x minus 4 equals 0, that is an example of a predicate. Now the classic thing we're going to do is we're going to turn a predicate into a statement by sticking on a quantifier. So some examples are, for every integer x, 2x minus 4 equals 0. That happens to be a false statement, and that's using the quantifier for all. And I'm going to remind you that for every and for all are often denoted with this upside down A symbol. Right? So that's for every or for all. Then my second example here is there exists an integer x, so 2x minus 4 equals 0. That happens to be true. There exists an integer that does the job, and that integer happens to be 2, but the existence of it is correct, right? So, and there exists is often denoted with this backwards E symbol. Okay, so these are predicates. Let's talk a little bit about quantifiers. We have 3 quantifiers. There exists, for all or for any, and there exists a unique. The existence quantifier gives me a true statement if there exists some value of the variable that makes the predicate true. So for instance, there exists an x in the integers, such that 2x equals 4, right? That's a true statement. A different quantified statement with the existence quantifier that's false is there exists an x in the real numbers, let's say, such that x squared is negative. That's false, right? It's impossible to have x squared be a negative number if x is a real number. Okay, the for all quantifier is requires it to be always true. So for instance, for all x in R, x squared is greater than or equal to 0. This is a true statement. But for all x in Z, 2x equals 4, that one's false. Right? It's not true for every x, it's only true for some x's. There exists a unique is an interesting one, because that one requires the statement to be true for some value of x. The predicate needs to be true for some value of x, but there can be only one such value. So for instance, this is true. There exists a unique x in the integers such that 2x equals 4. Right? The only solution to that equation is 2. Right? So there exists a unique such x. However, if I said there exists a unique x in the integers so that x squared equals 4, that becomes false. Right? That's false because I can take x equals 2 or x equals negative 2. So it's not unique. So that exclamation point stands for uniqueness. Okay, going back to axiomatic systems. An axiomatic system, as you remember, has the two things we talked about previously. We have the undefined terms and we have the axioms. Out of these, we build stuff. So the things we want to build are theorems. A theorem is a statement for which we have a proof. So I just begged the question there. A proof is a sequence of statements, of true statements, where each of the statements follows from a previous statement in the proof, or from the axioms, or from a previously proved theorem, or combining these things using the rules of logic, or things like that. Right? So it's basically a evidence that the theorem is true by giving a step-by-step process to establish why it is true. We usually introduce another kind of object, which is something called a definition. Now, a definition is a tool of convenience. It is not sort of a fundamental object in an axiomatic system. And a definition is basically a name that we give something with a collection of properties. And it's usually done for the purpose of convenience and for ease of communication. The one thing that's essential in a definition is the definition needs to be unambiguous. You need to know, is the object, does it satisfy the definition or does it not satisfy the definition? Right, so that's the one thing that's important when constructing definitions. A thing to remember, though, is there's a tension here in an axiomatic system between two competing goals. On the one hand, we want careful, detailed proofs. You want to give a step-by-step explanation of why the theorem is true. You want it to be watertight and impeccably rigorous. In some extreme case, you could imagine having a proof that was machine checkable, like computer checkable. On the other hand, right, so the other idea that's in competition with this is it's an act of communication. If I explain to you a proof that the square root of 2 is irrational, or a proof of the Pythagorean theorem, the key point is I want you to understand the proof of the theorem. So that's an act of communication. And communication and computer checkability of a proof are often fighting with each other, right? So if I'm explaining a proof to you, I don't want to get bogged down in the tedious details that are not important. I don't want to have all of my ideas sort of smeared out all over. I want to chunk them together so that they are organized in a way that makes it clear what the progression of my thought is. Right? So there's a certain amount of an art form in organizing your proof and including the correct information in the correct order, organized in a way that a human can read it and understand what is going on. I'll mention two examples of the rigorous extreme of this. Bertrand Russell and Alfred North Whitehead in 1910 published a work called Principia Mathematica. They later published, I think, a revision of it and then maybe a second volume. So this was a huge amount of work that they did. It took them hundreds of pages to prove that 1 + 1 = 2 in their framework. There's a contemporary mathematical project in the same, I shouldn't say the same vein, a similar vein, which is a goal to develop computer checkable mathematics for all of contemporary mathematics. They're using a piece of software called Lean. Lean was originally developed by Microsoft in order to help check that computer programs would be guaranteed to give the correct answer. And it's been leveraged now to work on these mathematical proofs. Okay, so coming back to this idea of communication to humans, we often organize theorems into levels of importance. Right? As I said before, in the axiomatic system, a theorem is a statement that has a proof. We normally think of the word theorem as meaning an interesting or important statement that has a proof. So we're going to sometimes use the word theorem to mean have this additional value judgment associated to it. And when we do that, we refer to a lemma as being, right, so it's a theorem in the axiomatic system sense, but a lemma is a true statement that has a proof that we think of as having maybe secondary importance. It's something you should think of as being scaffolding on the path to proving the main theorem that you're interested in. Now that said, there are many things that are called lemmas for historical reasons that turned out to be more important than whatever theorem they were being used in the proof of, right? So this value judgment is, it's a flawed human interpretation of mathematics. It is not really part of the logical structure of it. And now a proposition can mean many different things. In mathematical logic, it means a statement. We're going to forget about that for this class. A proposition for us is basically a synonym for a theorem. This is in large part because Euclid used the word proposition for most, if not all, of the theorems in the Elements. And in contemporary mathematical usage, I would say that it's often used to mean something that's maybe a little bit too big to be a lemma, but still not the main theorem of what you're trying to do. Or it sometimes is a theorem that's adjacent to a definition to help give some understanding to the reader of what the purpose of your definition is. Right? So it's a theorem that has some purpose, but it's not the main theorem of your work. Okay, but don't worry about these distinctions too much. Just at some level, theorem, lemma, and proposition are all synonyms. They mean a true statement that admits a proof. Okay, so let's quickly recap what we have in an axiomatic system. We have the following ingredients. We have undefined terms, we have axioms, we have definitions, we have theorems that can also masquerade under the names of lemma or proposition, and we have proofs. So I want you to think of this by analogy to a game. Let's say the game of chess. The undefined terms might be the players. Right? The rules talk about white and black, but if I'm going to play a game of chess with you, I could be white, you could be black, or I could be black and you could be white. Right? When you're playing chess, you get to choose who gets which side of the chessboard. The physical board is something that you can think of as an undefined term. Right? I can play chess on a board on the computer. I can play it on an actual physical board. I don't have a physical board here, unfortunately. You could have a board that's made up of a weird set of colors, right? You might imagine a beautiful wooden board where one color is made out of oak and the other one is made out of some contrasting kind of maple. Neither of them is black, neither of them is white, but you can tell them apart, and you and the person you're playing with can decide how to interpret those two colors. Okay, or if you prefer something more prosaic, a board with red and green squares. Right, so in that sense, the abstract rules are talking about an abstract chessboard. And when we actually play the game, we have a concrete physical chessboard. So we want to do this exact same thing in the context of an axiomatic system, which leads us to the question of how do we play an actual example of a game on the axiomatic system. So for this, we're going to talk about a model. A model of an axiomatic system is something you should think of as like a concrete realization of the axiomatic system, just like my chess example, right? Where if I have a physical board that's a physical representation of the abstract idea of the chessboard. Similarly, in the case of a model, we can interpret the model by having two things. One of them is an interpretation of what all the undefined terms are. So for that, we specify what the undefined terms mean in our model. And the second thing we do is we make a verification that the axioms now are true statements about whatever our interpretation was in the model. Right? So we need to show that the axioms of the axiomatic system are theorems in the model. So let me give some examples. The first example is teaching arithmetic to kids. Right? So if I tell you 2 + 1 = 3, that's at some level of abstraction that maybe, I'm not sure when the correct age is, maybe a 4-year-old is not really ready to understand. Instead, what we do is we start with a model where we say something like 2 cookies plus 1 more cookie is 3 cookies. So in that sense, cookies give a concrete model of addition with the positive integers. I should point out that this is a little bit tricky, right? You need to choose the model appropriately for the object you're looking at. Cookies do not give you a good model for the real numbers because it's not clear at all what root 2 cookies should be. And that's not a natural operation on cookies. Instead, maybe for the real numbers, it's more natural to look at a number line or distances, something like that. Right, so the different things can be models, multiple different things, right? I can look at apples instead of cookies. That gives me a different model of addition with the positive integers. But we can do all sorts of things to find models. For instance, moving squares on a game board. That's another model of addition on the positive integers. Okay, so this idea of axiomatic system with undefined terms has proved to be incredibly fruitful in mathematics. I had a hard time finding out exactly when the idea first entered into mathematics, but I can give you some examples of places where it's proved to be very useful. And I have here, I know that Peano introduced an axiomatic system for the positive integers in 1889. And Hilbert revisited Euclidean geometry and developed this framework to revisit Euclidean geometry. So we're going to owe a lot to Hilbert's 1899 work on Euclidean geometry. And he famously emphasized the importance of undefined term. So some examples that I have here, geometry. We usually, or following Hilbert, we think of geometry as an axiomatic system where point and line are undefined terms. We're going to have more of them. In set theory, that you studied a little bit of in Math 305, you had an intuitive idea of what a set is, but really what we do in set theory is we take a set and an element of the set to be undefined terms. Also, if you've done any linear algebra, abstract linear algebra, a vector space and a vector are undefined terms. If you've done some group theory, for instance, if you've taken Math 525, a group and a group element and the group operation, those are things that are undefined terms in that context. And of course, there are many, many, many more examples throughout mathematics of these axiomatic systems where we have undefined terms with axioms that they relate how these things fit together. Our next topic here is a simple model of an axiomatic system, something called incidence geometry. So this is going to be a super simple collection of axioms. If you think of the analogy to a game, right? If you think of chess, there are a whole mess of rules in chess. It tells you how every one of the pieces move, how you capture, when you're allowed to castle, how pawns move, all these things, right? So there are a lot of rules in chess. So if you wanted to think of chess as an axiomatic system, you would have a large number of axioms. Instead of that, we're going to look at a much simpler axiomatic system where we only have 3 axioms. So this would be analogous to saying, okay, we're going to think about a game where you have 2 players and they take turns playing. And maybe that's the only rule you have, right? That's a silly game, but if we can understand that, we can then use our understanding to build further and understand more deeply the axiomatic systems involved in Euclidean geometry. Okay, so let me explain what this incidence geometry is from the get-go. We have 3 undefined terms. We have point and line. Those are 2 undefined objects. And then we're going to have a relation, incidence relation, between a point and a line. We're going to introduce some definitions just to make our language a little bit easier. We're going to say that 2 points are distinct if and only if they're not equal to each other. We're going to say that 3 points are collinear if there exists a line so that all 3 of them are incident to that same line. And so 3 points P, Q, and R are collinear if and only if there exists a line L such that P, Q, and R are all incident to L. And then finally, we introduce this word non-collinear, which is just the negation of collinear. So 3 points are non-collinear if and only if they are not collinear. And now we have the axioms. Right? We have the undefined terms, we had some definitions for convenience, and now we get to the axioms. So the first axiom is that for every pair of points, of distinct points, there exists exactly one line L so that both P and Q are incident to L. And so that's existence and uniqueness of a line. Incidence axiom 2 says that for every line, there are at least two distinct points incident to that line. And then finally, axiom 3 is that there exist 3 points that are non-collinear. Any model for this kind of axiomatic system will be called an incidence geometry. Now, unlike Euclidean geometry, so this is Euclidean geometry, there's a deep theorem that any model of Euclidean geometry is essentially equivalent to any other model. In this case, we're going to have many inequivalent models. Now, I haven't defined equivalence of models of a geometry, so for now that's going to remain a sort of undefined intuitive statement rather than a precise mathematical one. So there are many examples of incidence geometries. Just to give some examples, there's an example that has only 3 points in it. It has 3 points and 3 lines, and that's it. There's an example for, well, there are actually many examples for if you give me an integer greater than or equal to 4, there are going to be multiple incidence geometries with n points in it. We'll look at one example of them. There's something called Fano's geometry. That's a pretty strange looking geometry. And then there's the Euclidean plane that you know and love from Euclidean geometry. So let's talk about the 3-point geometry first. So let's say we have 3 points, and we're going to name them A, B, and C. And the lines are sets of 2 points. So in this case, I have AB, AC, and BC. And we're going to say that a point is incident to a line if and only if it is contained in the set. So let's maybe draw a representation for this. If I take, right, this is, we have 3 points. I think of A, B, and C. And I'm thinking, let's say that line is green. I'm thinking of that as the set with those 2 points in it. And maybe this one is purple. And finally, let's say we take pink here. That is pink. Right, so we see that there is no line that contains all 3 points. So axiom 3 is verified. Axiom 1, we say that for any pair of points, there's a unique line passing through them. Well, that's almost by construction. And then finally, what the second axiom is that every line has at least 2 points incident to it. In this case, every line has exactly 2 points incident to it. Okay, and we can do basically the same thing with n points for arbitrary n. So consider here we have, I'm going to take, I don't know, n equals, what is that? N equals 5. Then what I'm going to do is I'm going to say that every pair of points gives me a different line. And so that gives me a line. 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 This gives me a line. That gives me a line. That gives me a line, etc. And I get, in general, I'm going to have n choose 2 many lines. Right? I haven't quite finished this job. Maybe I missed one. I'm not sure. 5 choose 2 is 10, and so that's maybe a lot to stick on this picture. Okay, so that's another example of an incidence geometry. We get a different one for each value of n. Okay, we'll talk about the Fano plane in a later video. For now, let's just talk about the Euclidean plane also as an example of an incidence geometry. So here we're going to think of a point as being just a point of Euclidean geometry, a line as a line of Euclidean geometry, and incident means, the usual a point being on the line. Okay, so the first axiom is any two distinct points, there's a unique line. Yes, that's true in Euclidean geometry. Any line has infinitely many points on it, so that's at least two. Axiom 2 holds. And we can find infinitely many triples of non-collinear points. Right, so I can put something like that. Right, that's an example of a triple of non-collinear points. Okay, so now let's go ahead and see if we can prove some results in incidence geometry. So the first thing we want to do is we want to think about how to organize a proof. So let's say we want to prove a theorem that takes the form hypothesis implies conclusion. Right, that's my H implies C. Right, H implies C. H is the hypothesis, C is the conclusion. So the way to prove something like that is we want a sequence of steps that start with H, where we assume that H is true, and then conclude at C. And each step should be justified by a reason. So there are a number of different ways of presenting a proof. We can do something that's sort of a classic of high school geometry, which is one of these so-called two-column proofs. We'll do an example of that in a little bit. We can follow the way Euclid wrote his proofs. So I'm not sure what Euclid did in the original Greek, but in the, modern translations of it, it's usually done with a parenthetical explanation. So there's an assertion, and then in parentheses, you explain the justification for that assertion. And then there's what's done in contemporary math research papers, where an explanation is given only for the difficult steps. Now, the difficult part of that is what's a difficult step depends on who's reading it, and skipping over a step that you think is easy is an opportunity for making a mistake. So one needs to be careful with that, but with enough practice and experience, that's sort of the style of writing of proofs that is done at a professional level. Okay, and what are possible justifications? Right, I said we want to have each line in a proof needs to be justified. So we can justify it because we assumed it was true as part of the hypothesis of the theorem. It might be true because it is an axiom or a consequence of an axiom. It might be true because it's something asserted by a previously proved theorem. It might be true because we are unpacking a definition. Right? We're using a definition to tell us what that means. We might be using an earlier step in the proof that we're in. Or we might be using a rule of mathematical logic. For instance, applying De Morgan's laws or taking the contrapositive of the statement. Okay, so in practice, because this gets very cumbersome if we have to do every single little detail, once we have a kind of argument that we've done a lot of or are very comfortable with, we can skip some steps or merge several of these steps together in one go. Right, so as I said before, a proof is an act of communication between humans. So we often include some logically unnecessary structural statements and sentences along the way to help give the reader an idea of where we're going or why we're doing what we're doing. So that I think you'll pick up just by example, right? We'll see enough examples, and then that's something I think you will internalize from that. And also from thinking about what would you like to see, what would you have liked to have seen written in a proof? That's the kind of thing that should inform the details that you put in your own proofs. Okay, in terms of formatting, we're usually going to start a proof with a statement, either proof, or if it's immediately following the theorem that we're trying to prove, or maybe proof of theorem number such and so, or proof of the Pythagorean theorem, or whatever. So we bring attention to the reader, look, we're now proving this theorem. We're going to end the proof either with this box symbol right here, or with the letters QED. QED is from the Latin quod erat demonstrandum, which means that which was to have been proved. Some people in some contemporary writers of mathematics, instead of using QED, will end a proof with a statement like as required, or as needed, or the result now follows. You want some kind of statement to say, okay, reader, you're done reading the proof. It's complete. And this box is also quite often used. And then sometimes we break up intermediate chunks of the argument into little subheadings. So, for instance, you might see claim, and you make an assertion there, and then underneath the claim you have a proof of that assertion, or maybe use indentation or cases or things like that to give some structure to the proof. Okay, an important class of examples of proof are proofs by contradiction. So one way of proving P implies Q is to assume that P and not Q, and I think this is unclear, right? So if P and not Q are simultaneously true, then something false has to happen. And so if we can do that, then that shows that P must imply Q. So for instance, the classic proof that root 2 is irrational is done by contradiction. You assume root 2 is a rational number, you do a bunch of work, and you end up with a contradiction, meaning you have simultaneously a statement and its negation have to be true simultaneously. That's not allowed, therefore your assumption was false. We'll do an example of it in a moment. Okay, so here's our first theorem from incidence geometry. If L is a line, there exists a point P so that P is not incident to L. So I'm going to remind us of our incidence axioms. Axiom 1 is for every pair of points, there's exactly one line incident to both of them. Axiom 2 is there are at least two distinct points that are incident to any given line. And the final axiom is there exist 3 points that are not collinear. So let's think for a moment about what our theorem is saying. And so we want to show that if we have a line, we can find at least one point that is not incident to that line. So let's think about why that should be true. And I think there's a good general strategy, which is that you want to restate your theorem typically in the form hypothesis implies conclusion. This is kind of a rule of thumb. It's not 100% going to work like this, but that's a good strategy in setting up a proof like this. Then I would say another important step is to unpack what the hypothesis means. In our example here, that's not so interesting, but if the hypothesis involved something involving a definition, it's often good to think about what does that definition tell us about the properties of the object. Okay, and then you need to identify what is your conclusion. Okay, so here my hypothesis is that L is a line, and the conclusion is there exists a point P not incident to L. As I said before, there's really nothing to unpack in terms of definitions here. And then finally, in order to prove the result, we either need to exhibit this point P that is not on my line L, right? We're given a line L, construct a P that's not on it, or the other option is if P doesn't exist, then we get a contradiction, right? Those are sort of the two general strategies that we should keep in mind as having. So let's take a look at it. I'm going to explain two different ways of proving this. And the first proof, we're going to look at it in two different ways. So let's first do a direct proof, Euclid-style. So by that I mean the justification for each statement is in parentheses at the end of the sentence. So I start with a line, and I'm naming it L naught. And so let L naught be a line. That is the hypothesis. Right? I want to show that for every line, there is a point that is not incident to it. So I'm saying, let L naught be a line. Then, okay, the next thing is we're going to invoke axiom 3. There exist 3 points, which we call A, B, and C, that are not collinear. So, yes, that are not collinear. They're non-collinear. That's what axiom 3 told us. Okay, so now I'm going to unpack that definition of non-collinearity. There does not exist a line so that A, B, and C are all incident to that line. Right? That's what it means to be non-collinear. So now I'm going to use De Morgan's laws to change this statement that's saying not there exists blah, 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 to for every line not A, B, and C are incident to L. So actually, it's using De Morgan's laws twice here. So for every line L, at least one of A, B, or C is not incident to L. Right? So that's using De Morgan's laws in order to get an equivalent statement. Now that's a statement for every line, so we can specialize it. In particular, for L naught, at least one of A, B, or C is not incident to L naught. This exhibits the required point P. Right? So we found one of A, B, or C does the job. So we've proved something a little bit better than the claimed theorem, but that's enough. We were able to prove the conclusion using this argument. Okay, so here's the same, basically the same proof using the two-column format. Right, so we start with let L naught be an arbitrary line. That's my hypothesis. There exist points A, B, and C that are non-collinear. I just restated axiom 3. There does not exist a line incident with all 3 of A, B, and C. That is my definition of non-collinearity again. For every line L, not all of A, B, and C are incident with L. That's De Morgan for quantified statement, and I guess also on, oh, I broke down the De Morgan in 2 steps here. In the previous proof, I'd done it in 1. Right, so then 5 follows from 4 by De Morgan's law. And then finally 6, we observe that the point, the one of A, B, or C that's not incident with L naught, we're naming that point P. This gives us the existence of the point P not incident to L naught, which was what we wanted to prove. Right? So this last line is just a restatement or a summarizing of what we ended up with. Okay, that's basically the same proof twice, just presented in different clothing. Let's take a look at the proof, a different proof, using a proof by contradiction. So this one I'm going to do in the, I guess, the style of just writing it in a paragraph form. So let L naught be a line. And now we need to warn the reader. We proceed by contradiction. You want to say something to warn the reader about what's going on. Assume there does not exist a point not incident to L naught. Right? This is our contradiction assumption. Then for every point Q, Q is incident to L naught. Right? That's the negate, right? There does not exist a point not incident to L naught. That means for every point Q, Q is incident to L naught. That's De Morgan's law for quantified statements. Then in particular, each of the 3 points from axiom 3 are going to be incident to L naught. Right? For all, so we're specializing this quantified statement, the for all to each of the 3 points from axiom 3. But then that means that all 3 points are on the same line L naught, so that contradicts the fact that they are non-collinear. That shows that our assumption was false, and therefore there must exist a point not incident to L naught. And we can go ahead and give ourselves the little box of the end of the proof. Hopefully that's clear, and don't hesitate to let me know if you have any questions. You have a similar proof to do on your first mastery homework.